All right, students, we are discussing the periodic trends in the periodic table or trends in the periodic properties, right? So, in the previous lecture, we have finished with the trends or variation as we go along the period or across or down the group in a periodic table for atomic radii, right? At the same time, we also have discussed about the ionic radii, covalent radii, etc. Today we have to start our discussion from ionization enthalpy. What is ionization enthalpy? So first of all, let me tell you, it is the amount of energy required to remove one electron from the outermost shell of a neutral gaseous atom. The condition is atom should be neutral and gaseous. Neutral so that no positive charge or negative charge is there and no force of attraction or repulsion will be suffered by the electron. And if it is gaseous, it means no neighboring atom will influence the electron, right? Then the amount of energy with which electron is associated, okay, just that much you already have studied in the structure of atom in the Bohr's radius and Bohr's energy for the electrons, that electron is associated with some energy which is generally negative in the orbits while revolving in the orbits. So to remove that electron, almost same amount of positive energy will be required so that we can pull out that electron, right? So suppose there are many shells. Then the first electron which you can remove will be the outermost electron, okay? As soon as you will, when you will remove first electron, the energy required, the amount of energy required to remove first electron will be known as IE1, that is first ionization enthalpy. All right. Now, as soon as one electron will be removed, this particular atom A will be converted into A plus. If further one electron is removed, okay, then the amount of energy required to remove one electron from the outermost shell of a neutral gaseous monocation, okay, एक बार atom मतलब +1 charge आ चुका है, after that you are removing the one more electron, right? The energy required in that case will be IE2, that is ionization enthalpy 2. And keep this thing in your brain, beta, that always first ionization enthalpy is minimum. Second ionization enthalpy greater than first, third ionization enthalpy greater than second. Okay? Let's see the NCERT lines about this concept. A quantitative measure of a tendency of an element to lose electron is given by ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom, okay, in the ground state. In other words, the first ionization enthalpy of an atom, of an element X is the enthalpy change for the reaction depicted in the equation. X gives X plus electron, okay? Just amount of energy required to remove one electron, clear? The ionization enthalpy is expressed in units of kilojoule per mole. Kilojoule per mole, okay? In general, we are using this unit, kilojoule per mole, to define the ionization, express the ionization enthalpy. We can define the second ionization enthalpy as the amount of energy required to second most loosely bound electron from a cation. All right, as you can see in this reaction, X plus gives X2 plus, and further one electron is removed. Clear? Energy is always required to remove electron from an atom, and hence ionization enthalpies are always positive. Any atom will not lose electron itself. Clear? Even if it has a tendency to lose electron, then also it will not have a negative value. So although the ionization enthalpies have always a positive value, the second ionization enthalpy will be higher than the first. I have already told you about this. The second ionization enthalpy will be higher than the first. The ionization enthalpy, because it is more difficult to remove the an electron from a positively charged ion. होता क्या है बेटा, as soon as the positive charged ion is formed, suppose ये आपका normal atom है, this is nucleus, second orbit, right? Nucleus is having some amount of positive charge. Electrons are revolving around. Okay, when you will remove first electron, then that much positive charge was distributed, distributing the force of attraction in 4 electrons. Now one electron is removed. Okay, so जो एक इंडिविजुअल इलेक्ट्रॉन के हिस्से में पॉजिटिव चार्ज का फोर्स ऑफ अट्रैक्शन आ रहा था, उसे आपने ओवरकम कर लिया. Now that positive charge, only positive charge is not going to change because it is proton and present in the nucleus. So same positive charge will attract now 3 electrons. Okay, so जब वही चार्ज 4 इलेक्ट्रॉन को अट्रैक्ट कर रहा था और वही चार्ज 3 इलेक्ट्रॉन को अट्रैक्ट कर रहा है, so you can easily understand that the force of attraction is now higher, and to remove the electron now more energy will be required. Okay, so from this concept you can easily understand that the first ionization enthalpy was always less than the second ionization enthalpy. In the same way, the third ionization enthalpy, right? So the first ionization enthalpy of elements having atomic number up to 60 are plotted in this figure. Let's see this figure so that you will be able to understand and you will be able to draw some mind map in your brain, right? See here, students, atomic number and ionization enthalpy. We are getting the peaks at, well, सपोज फर्स्ट 10 का देखते हैं पहले, फिर फर्स्ट 60 वाला बाद में देखेंगे. ओके, ये 60 के लिए है, ये फर्स्ट 10 के लिए है. लिथियम, देन बेरिलियम, बोरॉन, कार्बन, नाइट्रोजन, ऑक्सीजन, फ्लोरीन, नियॉन. ऑलराइट, अगर मैं इनके इलेक्ट्रॉनिक कॉन्फ़िगरेशंस लिखूं तो आपको बहुत आसानी से समझ में आ जाएगा. लिथियम, व्हाट इज इट्स एटॉमिक नंबर? 3. ओके, सो लेट मी राइट फॉर लिथियम, देन बेरिलियम, all right, boron, carbon, nitrogen, oxygen, fluorine and neon. All right, please keep paying attention here only. Your lithium is 2s1. Okay, I'm writing just outermost electronic configuration, 2s1, 2s2, then we are having 2s2 and 2p1, right? For carbon it is 2s2 and 2p2. For nitrogen it is 2s1 and 2p3. All right, oxygen is 2p4, fluorine is 2p5 and neon 2p6. मैं जब डायरेक्ट p लिख रहा हूं तो इसका मतलब s में इलेक्ट्रॉन ऑलरेडी जा चुका है. ठीक है, now see the trend. Lithium is having minimum value. This is a period, this is your third period, sorry, second period, right? From lithium to neon, second period. In the second period, minimum ionization enthalpy value is given for which element? Lithium. Okay, and maximum is for neon. It means when we go along a period, ionization enthalpy value keeps on increasing. Okay, But is this increase a constant increase? No, this is not a constant increase. From lithium to barium it is increasing, then we can see a decline. Barium to boron, there is a decline. Boron, carbon, nitrogen increasing. Nitrogen to oxygen, there is a decline again. Oxygen, fluorine, neon. Then why? What is the reason behind this? The reason behind this is their electronic configuration. Let's see. Beryllium to boron. In case of beryllium, we are having 2s2. S orbital having 2 electron, quite stable. To remove 1 electron from a stable orbital is quite a difficult task. But here, in p orbital, only 1 electron is present. Right? And you know very well, in a bigger orbital, a single electron is very unstable thing. Okay? So this electron is easily removed. Means the amount of energy required to remove 2p, 1 electron, first electron of 2p, right, is lesser than to remove the paired 1 electron from the pair of 2s. Understanding? That's why beryllium के comparison में boron का first ionization enthalpy is lesser. Now move to boron to carbon, increase हो रहा है. Carbon to nitrogen, increase हो रहा है. In case of nitrogen, 2p3, we have got a completely half-filled orbital. And according to Hund's rule of maximum multiplicity, you know that orbital is more stable when it is completely filled or when it is half-filled. Completely half-filled, okay? In case of 2p4, what will happen? 1 electron will be added to px, means these two are, see, this was a stable situation. Right? And further 1 electron is added here. It is causing instability, and something causing instability, atom want to get rid of it. Right? Understand what I'm saying? So this electron will be removed easily. That's why from on moving nitrogen to oxygen, we can see a decline in the first ionization enthalpy. All right? And second ionization enthalpy of oxygen will be very high. Why? Because after removing 1 electron, you are getting a cation as well as you are getting a stable configuration of P3. Right? So second ionization enthalpy of oxygen will be very high as compared to others. But that is not my point of discussion right now. So this is clear. Now move to from oxygen to fluorine. 1 more electron is present. It's okay. Let it be present. After that, neon. In neon, you are having 2p6. I have already told you that to remove electron from a completely half filled or from completely full filled is quite difficult. Why? Because in case of complete half filling or complete full filling, the orbitals are stable. Understood? So this trend you people are able to understand. Along a period, ionization enthalpy is increasing. There are some fluctuations, but those fluctuations are because of the electronic configuration. Clear? Now, we will see a trend down the group. Here we have plotted for group 1, that is your alkaline, alkali metals, lithium, beryllium, boron. I'm sorry, I just lost my concentration here. It is not boron here. Just wait a minute. Lithium, then sodium, right? In first group I'm talking. Lithium, sodium, potassium, rubidium, cesium. Further, if you are interested, francium, but francium is, radioactive, so don't consider it right now. Yes. Now, lithium, electronic configuration outermost 2s1, sodium 3s1, potassium 4s1, rubidium 5s1, and cesium 6s1. It will not overlap, but let it be, okay? So let's see. In case of lithium, your electron is, let this be, this point be, this black point be your nucleus. Okay, then first orbit 1s1, second is 2s1, means your electron is present here in the second orbit. In case of sodium, your electron is present in third orbit, outermost electron. In case of potassium, it is present in fourth orbit. In case of rubidium, it is present in fifth orbit. And in case of cesium, it is present in sixth orbit. You know which force of attraction is working between nucleus and the electron? Electrostatic force of attraction. Electrostatic force of attraction is the non-contact force. All the non-contact forces in this universe follow the inverse square law, right? It means as the distance from the nucleus will be increasing, the force of attraction by which the nucleus is binding the electron will keep on decreasing, right? It means that the most easy task is to remove the electron from the outermost shell of the cesium, right? So cesium will have minimum ionization enthalpy, and it is very difficult to remove the electron from lithium as compared to cesium. Why? Because the electron is present in a lower orbit. Lower orbits, electrons are attracted by the nucleus with greater force, right? So lithium is having the maximum value of inertia enthalpy. It means down the group, inertia enthalpy keep on decreasing. Along a period, inertia enthalpy keep on increasing. Clear? Any problem? I hope it is clear to all of you. Let's move forward. One phenomena I have to tell you. This is called shielding or screening. What is shielding or what is screening? I will have to draw the same thing again. Just wait a minute. Let me get a whiteboard. Let it be an atom of some huge atomic number. Let it be radon. Okay, radon. Atomic number 86. All right. In the first shell, how many electrons are present? 2 electrons. All right. In the second shell, 8 electrons are present. In the third shell, 18 electrons are present. In the fourth shell, 32 electrons are present. In the fifth shell, how many? Yes. 18 electrons are present. And in the sixth, there are 8 electrons. What is the sum? Just let's check if it is 86. Yeah, 10 and 50, 60. Yeah, it is 86. All right. So here we can have some other perception as well. Like 8 electrons are attracted by 86 protons. In case of neon, this is your radon, the last noble gas, sixth noble gas. And in case of neon, two electrons are present in the first and 8 electrons are present in the second. Neon is having 10 protons. So 10 protons are attracting 8 electrons. Here 86 protons are attracting 8 electrons of the outermost. Then according to this perception, radon must have a higher ionization enthalpy, right? But these electrons which are present in the inner orbitals, inner orbits, okay, the electrons which are present in the inner orbits, like these 8 electrons, these 18 electrons, 32, 18, they are causing some shielding effect. Okay, what is shielding? They are shielding the outermost electron from getting attracted by the nucleus. That's why it is easy to remove one electron from the outermost shell of radon atom as compared to from the neon atom, right? That's why as we go down the group, the ionization enthalpy keeps on decreasing. So this effect, okay, which is which due to which the force of attraction due to the nucleus on the outermost shell of outermost electrons keeps on decreasing or is decreased by the penultimate electrons. Penultimate means uske pehle ke electrons, right? Andar ki orbits ke electrons. This is called the shielding effect. Clear? Shielding effect or screening effect. Fine. Let's move on. You people can go through this just once, it will be more than enough. I have already explained all these anomalies, okay? See the example 3.6. The first ionization enthalpy values of the third period elements sodium, magnesium, silicon are represented or respectively 496, 737 and 786 kilojoule per mole. Predict whether the first ionization enthalpy value of aluminium will be more close to 575 or 760 kilojoule per mole. Justify your answer. जो एल्यूमिनियम का फर्स्ट आयनिक एंथैल्पी होगा, सी इन दिस पीरियड वी आर हैविंग सोडियम, देन मैग्नीशियम, then aluminium, and then silicon. We know as we go along a period, what happens? Along a period, ionization enthalpy value increases. Okay, so sodium's value is 496, magnesium is having value 737, and silicon is having value 786. Then what will happen to the first ionization enthalpy of aluminium? It is around 760 or around 575. Let's check. As you can see, it is lying between the magnesium and silicon. You may go for answer 760, right? But see the solution. It is more close to 575 kilojoule per mole. Why? Because the value of aluminium should be lower than that of magnesium. Okay, मैंने आपको बोला along a period ionization enthalpy increases, but at the same time I have given you some anomalies as well. Now when we move from second to the third, just now we have discussed the example when we were moving from in the second period after beryllium to boron, there was a decrease. Why there is a decrease? Magnesium is having outermost configuration 1s2, aluminium is having 1s2 2p1. I'm sorry, it's not 1s2, it is 3s2. 3s2 and 3p1. All right. So the one electron present in the p orbital is unstable. I hope all of you are getting me, right? The case is very similar as it was in case of beryllium to boron. This is your magnesium outermost electronic configuration 2s2, and this is your aluminium outermost electronic configuration is 2s2 and 2p1. So it is easy to remove this electron of the p orbital, because in a p is a big orbital as compared to the one electron, right? You are having just one electron in the p orbital, it is quite inappropriate thing. Okay, understanding what I'm saying? So your value technically, अगर आपने deep knowledge नहीं लिया है, you just have seen the trend that ionization enthalpy increases along a period, then you will go for 760. If you have a deeper knowledge, you will take the correct answer, that is 575. Understood? Now the next thing what we have to discuss is electron gain enthalpy. Let's see what is electron gain enthalpy. When an electron is added to the neutral gaseous atom to convert it into a negative ion, the enthalpy change accompanying the process is defined as electron gain enthalpy, right? The amount of energy generally releases, generally released. The amount of energy released when one electron is added to the outermost shell of a neutral gaseous atom, right? That is known as electron gain enthalpy. So, electron gain enthalpy provides a measure of ease with which an atom adds an electron. Ionization enthalpy में removal हो रहा था electron का, यहाँ पर addition हो रहा है, simple, okay? So X receives one electron to convert into X minus. Depending on the element, the process of adding of electron to an atom can be endothermic or exothermic. If an atom is having more tendency to get an electron, right, the process will be exothermic, because by addition of the electron it will become stable, है ना? On the other hand, suppose आपके पास फ्लोरीन जैसा कोई एटम है जिसको एक इलेक्ट्रॉन चाहिए, it is having 7 electrons in its outermost orbit, right? It is having 2p5 electronic configuration. Just by getting one more electron it will become 2p6, and you know 2p6 is stable, right? So it will be an exothermic process. ये इलेक्ट्रॉन रिसीव करके हीट रिलीज कर देगा, एनर्जी रिलीज कर देगा, and it will become stable. F minus will become stable. Okay. On the other hand, आपके पास सोडियम जैसा कोई एटम है, राइट, और आप उसको इलेक्ट्रॉन देना चाह रहे हैं, उसके पास ऑलरेडी आउटर मोस्ट सेल में 3s1 वन इलेक्ट्रॉन आउटर मोस्ट में है, वो उस इलेक्ट्रॉन को खुद देने की टेंडेंसी रखता है, राइट, बिकॉज उसके पहले उसके पास 2p6 है और वो 2p6 होकर के नियॉन जैसा स्टेबल होना चाहता है. आ रही है बात समझ में? सो अगर आप इसको इलेक्ट्रॉन दोगे तो वो आसानी से तो लेगा नहीं. फॉर दिस आपको एनर्जी खर्च करना पड़ेगा, मींस द प्रोसेस विल बिकम एंडोथर्मिक. ओके, सो इट डिपेंड्स अपॉन द एटम, ओके, एलिमेंट, that the process of addition of electron will be endothermic or exothermic. I hope you are getting this point. For many elements the energy released, just 1 minute beta, yeah, for many elements the energy is released when an electron is added to the atom and electron gain enthalpy is negative. For example, group 17 elements, सभी का electron gain enthalpy negative हो जाएगा. They have very high negative electron gain enthalpies because they can attain stable noble gas electronic configuration by picking up electron. On the other hand, noble gases, अब noble gas को आप electron दें तो वो तो नहीं receive करना चाहेगी, वो already stable है, तो उसके लिए positive values आएंगे. All right. This is a chart which is representing different electron gain enthalpy values. Just have a look on it and it is okay. You need not to learn these values. The electron gain enthalpy values of noble gases, you can see these all are positive values and highly positive. You can see these large positive values of electron gain enthalpies are because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration, right? It may be noted that the electron gain enthalpies have large negative values towards the upper right of the periodic table preceding the noble gas. Okay. The variation in the electron gain enthalpies of element is less systematic than for ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. Across a period, noble gases exception के तरीके ले लीजिए तो value keeps on becoming more and more negative as we move along a period. Okay. On moving from left to right across a period, consequently, it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. Okay, छोटे atoms में electron add करना is quite easier as बड़े atoms में add करना. Okay. हालांकि फिर से इसमें एक्सेप्शन आ जाएगा. आप लोग जरा हेलोजन सीरीज को चेक करें. ये देखिए फ्लोरीन टू क्लोरीन वैल्यू हाई हो रही है जबकि डिक्रीज होना चाहिए. फ्लोरीन सबसे छोटा एटम है, उसमें तो बहुत आसानी से इलेक्ट्रॉन अट्रैक्ट कर ले उसका न्यूक्लियस, जबकि क्लोरीन बड़ा एटम है, वहां पर कम आसानी से अट्रैक्ट करना चाहिए बट नेगेटिव वैल्यू ज्यादा है. इसका मतलब क्लोरीन के केस में ज्यादा एनर्जी रिलीज हो रहा है एज कंपेयर टू फ्लोरीन. द रीजन बिहाइंड इज फ्लोरीन का एटम में इलेक्ट्रॉन 2p में प्रेजेंट है, राइट. सेकेंड ऑर्बिट एक छोटा ऑर्बिट है एज कंपेयर टू द थर्ड ऑर्बिट. फ्लोरीन में आउटर मोस्ट शेल सेकेंड है, सेकेंड में ऑलरेडी 7 इलेक्ट्रॉन प्रेजेंट है, 8th आएगा तो थोड़ा बहुत आपस के इलेक्ट्रॉन्स में रिपल्जन हो जाएगा. अरे ये बात समझ में. जबकि क्लोरीन ऑनवर्ड्स वो साइज बड़ा हो जाता है और फिर कॉन्टिन्यूअस डिक्रीज हमें देखने को मिल रहा है वैल्यूज में. अंडरस्टूड. ये एक नोटेबल पॉइंट है यहां पर. क्वेश्चन देखते हैं इसका. विच ऑफ द फॉलोइंग हैव द मोस्ट नेगेटिव इलेक्ट्रॉन गेन एंथैल्पी एंड विच हैव द लीस्ट नेगेटिव. मोस्ट नेगेटिव एंड लीस्ट नेगेटिव. फॉस्फोरस, सल्फर, chlorine and fluorine. Just use your brain to get the answer. Pause the video. Now let's see the solution. Electron gain enthalpy generally becomes more negative across a period as we move from left to right. Okay, left to right आप जाएंगे तो it will become more negative. So let's see ये कहां पर placed है. In the second period we are having fluorine at the end just before the neon noble gas. Okay, below fluorine we are having chlorine, before chlorine it is sulfur, and before sulfur it is phosphorus. Understood. So within a group electron enthalpy becomes less negative down the group. जब हम नीचे जाते हैं तो वो less negative होती है. However, adding an electron to 2p orbital leads to a greater repulsion. ये देखिए मैंने आपको पहले बताया था. Than adding an electron to the larger 3p orbital. Hence the element with most negative electron gain enthalpy is chlorine. सिर्फ ट्रेंड्स को देखें तो उसके अकॉर्डिंग मोर इलेक्ट्रॉन गेन एंथैल्पी वाला आपका फ्लोरीन होना चाहिए, राइट. बट मैंने आपको बताया फ्लोरीन का साइज छोटा है एज कंपेयर टू क्लोरीन, तो ये एक्सेप्शन बन जाता है. सो मोस्ट नेगेटिव इलेक्ट्रॉन गेन एंथैल्पी वैल्यू इज ऑफ क्लोरीन एंड लीस्ट नेगेटिव बिकॉज आपने पढ़ा अलोंग अ पीरियड जब आप मूव कर रहे हैं तो आयनिक एंथैल्पी की वैल्यूज मोर एंड मोर नेगेटिव होती जा रही है. जब मोस्ट नेगेटिव ये है इट मींस ऑब्वियस सी बात है लीस्ट नेगेटिव फास्फोरस हो जाएगा. क्लियर. एनी डाउट्स हियर? फाइन. नेक्स्ट थिंग इज इलेक्ट्रोनेगेटिविटी. वेरी इंपॉर्टेंट कॉन्सेप्ट बेटा. I think electronegativity we will discuss in the next lecture. Till then, keep studying, keep watching the videos, stay safe and stay healthy. For school students, it's my request to join your school and become a COVID warrior.